So we're going to start by evaluating this like we normally would. I'd rewrite this as x to the negative second. I would take the antiderivative. And remember, the power rule for antiderivatives, you add 1, multiply by the reciprocal. Reciprocal is just -1. So it ends up being -1 over x. And we evaluate that from -1 to 1. That's what we're used to. Okay? And I get -1 minus +1, which gives me -2. Right? Simple enough. Just a quick review question. All right. Confirm that answer using your calculator. What? No, it's -2. All right, we just did it. Math 9, -1 to 1 of 1 over x squared dx. Divide by 0. That's strange. Super strange. Well, let's just maybe change up these numbers. Maybe the numbers. Let's go from -1 to 2. So -1 to 2. That'll be -1 minus. Sorry, that'd be -0.5 minus +1. So that'd be -3/2, right? Okay, good. Now go ahead and plug it in from -1 to 2, and we should see -3/2. I broke your calculator. This is insane. What are you talking about? It's so simple, right? Let's see here. -1 to 2. It's probably going to work on my fancy computer calculator. What? Tolerance? Probably total, not that, right? Tolerance on that? I don't know. Who knows? Gosh, it's working really hard. Well, why don't you go into y equals and graph 1 over x squared and tell me why we can't find the integral from -1 to 2. It's frozen, right? What happens when your calculator freezes? Do you know how to pause it? What's... No, there's a quicker way. You just press on, and it'll freeze, typically. Did it second on? It usually freezes if you press on, just in general. Oh yeah, there you go, break. So usually on will if you see that thing, it's working, you press on, it kind of breaks it. Or second on, I guess. Okay? So graph 1 over x squared. We're going to have to go back into function mode. And tell me why we can't do this. What's going on? What do we have on the graph? Or don't have? Does the graph ever connect up here? Can I plug in 0 into this function? Since I can't plug in 0 and can't be simplified, we have what type of thing? I'm thinking about a V and then an A. A vertical asymptote. We have a situation where I'm trying to add up all of this area going up to infinity. And then all the area coming back down from it until I get to 2. We have a situation where we're dealing with an infinite amount of area potentially. And all of a sudden, this is not the correct answer because we have a special situation. We have what we call an improper integral. This is our last lesson on improper integrals. And this was the one that we looked at using our calculator, where we have a vertical asymptote, which means we are going to cross over a vertical asymptote on our interval. And though the fundamental theorem of calculus says we're going to, just take the change in our antiderivative, turns out it's very, very, very misleading because we'd have an infinite amount of area. Okay? Well, there's another improper integral as well. A situation like this, where we have infinity as one of our bounds. And yes, we think that this would be an infinite amount of area, and we think that always this is an infinite amount of area, but what we will find is that in some cases, though we are looking at a vertical asymptote and close to it, and though we are looking out all the way over to the right in terms of x's, we will find that there is actually an area that we will converge to. We will be approaching a specific number. Okay? That's the whole, if you have an infinite amount of rectangles to calculate an area, you'd think your area would be infinity. But no, we would just be converging towards a finite number. Okay, so two types. This is an area with a boundary that approaches infinity. And this is a situation where your integral, deals with a vertical asymptote. Okay? And with these, we need to be very careful with the fundamental theorem of calculus. Just like we saw in that first one. Okay? We will be still using the fundamental theorem of calculus, but in a specific way. Okay? Now, what is going to help us evaluate these integrals are our friends that deal with infinities and approaching values and limits. Okay? And I'm going to give you two examples, the first two that we kind of saw, and we're going to see what they're equal to. Okay? Let's deal with this one on the left first. Okay? So we're talking about the area under 1 over x squared from 1 to infinity. Now, we do not like plugging infinity into expressions. Okay? It's more of a concept. We need to think about approaching infinity. Sometimes we do, but it's not always the best thing to do, best practices. So what we do is we rewrite the integral using limit notation. I will use b as kind of a placeholder for where infinity is. Okay? And then I will use the fundamental theorem of calculus, which means I will take the antiderivative of 1 over x squared, which we discussed was negative 1 over x, but we'd find the change between 1 and b. This is the limit as b approaches infinity. And then I would go ahead and plug in b and subtract 1 plugged in. Now, we know what the limit as b approaches infinity of negative 1 over b is. As the denominator continues to grow and grow and grow and grow, what is 1 divided by that huge denominator? Approaching. It's approaching 0, right? So we would say this is 0, and then I'd add 1, and turns out the area, the infinite area, starting at 1 and going to infinity under 1 over x squared will approach a value, and it will approach the value of 1. That's kind of insane to think about, right? Because we're going on forever. But we just continue to add values that get smaller and smaller and smaller and smaller. And all of a sudden, instead of adding, we are just getting closer to. Okay, we understand that. Well, now let's see what happens if I go from -2 to 1 from 1 over x squared. When I'm dealing with this, we need to use our friends the one-sided limit. Oh gosh, not now. Things are going so well. Okay. I will need to express this as a limit from -2 to b, but we will approach our vertical asymptote from the left side of the 1 over x squared. And then I will need to add the limit as b approaches 0 from the right side of b to 1. Okay? And now we have our friends the one-sided limit that deals with what things are doing as we're approaching a vertical asymptote. Okay, again, we would have the fundamental theorem of calculus that we can use to help us. This would be -1 over x from -2 to b, plus this will be -1 over x from b to 1. Okay, I split it into two different integrals that surround my vertical asymptote. And I look at approaching my vertical asymptote, which is at 0. Okay? And I'm still finding the limit as b approaches 0. So I get -1 over b minus, it ends up being plus 1/2. Then over here, I'd be adding -1 over 1 minus -1 over b. And correctly, this would be the limit as b approaches 0 from the right. I got to make sure I have that correct. Okay, now this is the limit as b approaches 0 from the left, and this is the limit as b approaches 0 from the right. Now we're plugging in an extremely small value that is negative in for b here. If I divide it into -1, what do I get? -1 divided by some extremely small negative value. Right, a huge positive value. Ms. Pena.
What happened to the x squared?
I took the antiderivative of it. And over here, if I plug in a very small but positive value in for b, and I divide it into -1, what do I get? A huge negative number. Now that we've evaluated it, and yes, I do have infinity here, but we're thinking about the concept. We know that it's growing. We have an infinity plus another infinity. Still going to be infinity. When we do infinity minus infinity, that's a problem. But this, thankfully, is infinity plus an infinity, plus a couple constants. This will be growing. So in one situation, we converged to a value. In another situation, we did not. You could either converge or diverge. with improper integrals. The idea of convergence and divergence is going to be what we're going to focus on for the remainder of the year in terms of new material. When will we have an infinite kind of summation, like an area, end up equaling a value, or when will we have an infinite summation end up just going off towards infinity? When will we continue to grow, or when will we not grow and approach a specific value? It's all we're going to talk about for the next 2 units moving forward. Okay? Right now, we're just going to talk about these improper integrals, and we're going to evaluate them. Here's another situation. We're talking with the boundaries that include the infinity, where we'll have something that converges and something that diverges. Let's do the diverging one really quickly. It's easier to do. It won't take that long. What is the antiderivative of 1 over x? Good. We remember that this is the natural log of x. Now, I'm going to be taking the limit as b approaches infinity of b as my interval. So when I take the antiderivative, you have the limit as b approaches infinity of the log x from 1 to b. I then will have the limit as b approaches infinity of log b minus the log of 1. We know that this will approach infinity. This will be approaching 0. Since we'll have infinity, we say this area diverges. So here's an example of, an area that will look just like 1 over x squared. 1 over x looks just like 1 over x squared when we're talking about to the right of 1. But in this situation, if I tried to add up all the area to the right of 1, turns out we continue to add values. And when we continue to add values, instead of it approaching a singular value, the values just continue to increase. And we'd actually be approaching an infinite area. We would not be approaching a specific value. And we just looked at 1 over x squared, and it approached an actual value. Kind of crazy to think. They look so similar, but the answers are so different. Okay? You kind of see that with your calculator. Let's do a little experiment. Go ahead and find the area from like 1 to 1,000 or 1 to 5,000 of 1 over x squared. And then do the area from 1 to 5,000 of 1 over x. And see if you can notice a difference. I'm hoping that we do. I've not done this before, so this might fail. Does it break the calculator? No. Nope, doesn't break the calculator. We're already at 8, and we've gone to 5,000. But let's look at 1 over x squared from 1 to 5,000. I told you that this area is going to approach and converge towards 1. And oh my goodness, it's getting closer and closer to 1. 2 things that look super duper similar, giving us very, very different answers. Okay? Convergence and divergence. This is the beginning of a bright future for the next 2 units. Okay, so let's talk about this guy. This guy's going to converge. Now, how do we deal with it? Looks like it's going to be a UDV situation where we need to use UDV. Now, and what you'll probably notice is that this whole limit thing seems really like unnecessary. Why don't we just take the antiderivative and plug in infinity, because I end up getting this same thing? Well, that's what I did back in the day. And I still do it now, but if you ever get a free response question, you're not going to get the correct points if you don't use a limit. Okay? Because we don't like to plug in infinity. We like to just think about the concept being plugged in. You understand? So for multiple choice, don't worry about the limit. Just antiderivative, keep infinity up here, have fun with it, right? But for free response, make sure you write the limit. Okay? Okay, so limit as b approaches infinity of integral from 2 to b of 1 minus x e to the negative x dx. Let's go ahead and use u dv. U will be 1 minus x. dv will be e to the negative x. du, negative dx, v, negative e to the negative x. Should have a dx up here. Okay, let's go ahead and rewrite things. So I'll have the limits as b approaches infinity of the antiderivative would be uv, so that's 1 minus x, negative e to the negative x, times, minus the integral, so b again from 2 to b, v du. So that'd be positive e to the negative x. Okay, well, I'm going to take this antiderivative, and then I'm going to worry about the b and the 2. So I'll have negative 1 minus x times negative e to the negative x. This will be the antiderivative negative e to the negative x, so this will be plus e to the negative x. This entire thing, I'm going to find the change between 2 and b. Limit as b approaches infinity. Okay. Sorry for being so cramped. Well, before I plug in b and before I plug in 2, I feel like I'm going to simplify this a little bit. I'll distribute this negative e to the negative x. I get negative e to the negative x plus x e to the negative x plus e to the negative x, the change between 2 and b, as the limit as b approaches infinity. Well, this actually helps me out tremendously because these cancel. Negative e to the negative x and the positive e to the negative x. So I end up with just a limit as b approaches infinity of x e to the negative x from 2 to b. And if you want to, probably what also is going to help to evaluate this is to write that as x over e to the x. Okay? Now I plug in b, I get b over e to the b minus 2 over e squared. The limit as b approaches infinity. Well, we have a situation where we have infinity over infinity, right? That's usually this indeterminate form. You don't ever know what infinity minus infinity is or infinity divided by infinity. But we actually do know what this is. If you remember our limits, when we're talking about infinities, it's all about the growth of our numerator versus our denominator, right? What's growing faster, what's growing slower? So what's going to grow faster, the numerator and the denominator? Right. You know, e to a power is definitely going to produce bigger numbers as we're plugging in bigger numbers than just, you know, x to the first power, okay? So the denominator is growing faster than the numerator. We know that this is going to approach 0. So this is 0 minus 2 over e squared. Guess what? This is a situation where our area will converge toward the value. Okay? All right. Your turn. Let's see if this converges or diverges If it converges, find the number that it converges to. Look at it. Think about it. What rule should I use to take this antiderivative? What do we want? UDV or U? Because it's going to be one or the other because this one's complicated. U. What are you setting U equal to, Ms. Pina? The negative x squared, because its derivative is a form of x, which means when we solve for dx, we'll be able to get rid of that x. We should always be careful, though, when we change from dx to du, we might have to change these boundaries, but it doesn't really matter in this case. Okay. Like that. So it is negative. Well, it is b squared, it is, but what's infinity squared? That's why I kept it as b. But you're right. It should be that, and it should be that, but it doesn't change that. Good. What else? Anything else? Do we all get that? Okay, let's do another one. Another one with these. Let's skip that one and do this one. Another one with infinity in our boundary. These are the most common ones you'll see on the AP test. It's rare, but it does happen sometimes that they will give you an integral that goes over a vertical asymptote. It's very rare because you're going so quickly through a test that students don't catch that, but it is possible. What do you think here? U, dv, or U? It's U again for this one. You select log x because its derivative is 1 over x, which will help me cancel this x in this denominator. Now, I'm not going to use my things right now. I'll wait till later. I wish it could automatically. Okay? You'll find when we do these, typically this will either be infinity or it'll be 0. Like, let's do like a very, very obvious one. And you guys can, kind of figure this out yourselves as well. Right? If I talk about the area under X, that's definitely not going to add up to approach a number, right? Well, we can kind of see, and a bunch of these have been converging in a row, but if I have 1/2 x squared, and just for simplicity's sake, I will skip the limit part. I have 1/2 infinity squared minus 0. Well, that's definitely going to be, approaching infinity. So a very, very simple and obvious example that this is going to be divergent. Okay? It's when we have functions that are going to approach 0, when we're adding smaller and smaller, what seems to be small and smaller values, that it actually becomes a question, and it becomes not a simple matter of, yes, this will approach a value, or no, this will not approach a value. And it becomes a very large part of mathematics, like convergence and divergence. And we'll just scratch the tip of it in the next 2 units. Okay, so got that. This was a fairly tough one. Go ahead and tackle that. What if it's D? So usually it's not D. I'll tell you that right now. Okay? Not saying it's never D. I'm saying for problems like this, students like to just go with D, and that's when they're wrong. Looks like you substitution again, right? It's not. UDV. Okay. I'm going to skip the whole limit part. Don't skip the limit part on a free response question. This is just a constant, so I can take the antiderivative of it. So it'll end up being positive 1/4, so I'm still subtracting a 1/4 k e to the negative 2x between 0 and infinity. Are you with me so far? Okay. So we rewrite this as negative 1 over, or negative kx over 2 e to the 2x. We can rewrite this as k over 4 e to the 2x from 0 to infinity. If I plug in infinity, this will be infinity over infinity, right? But this is going to be going slower, and this will be going faster because it's e to a power. So this will be approaching 0. Then minus, this would be, again, I'm plugging in infinity, another 0. But now I minus whatever 0 is plugged into. I'd have 0 over 2 here, because it's 2 times e to the 0. So it's 0 over 2 e to the 0, which is 0, minus k over 4 e to the 0, which would be k over 4 times 1, e to the 0. And this all equals 1. Equals 1. So this is just positive k over 4 equals 1. What is k? So it wasn't D, it was C. Close. Okay? Now you will sometimes see a question like this guy. Usually it's not this obvious. Sometimes it will be this obvious. You say, why is this not 3/8? Well, go ahead and use the fundamental theorem of calculus, and you'd see that the fundamental theorem of calculus would tell you that it would be 3/8, but that's wrong. I'll show you that real quick. It's x to the negative third, so this is negative 1 over 2x squared from negative 1 to 2, and you'd get negative 1 4/8, 8 minus negative 1/2. That's negative 1/8 plus 4/8, so that's 3/8, right? You'd think 3/8. Wrong. It's a vertical asymptote that's at 0. We would do the limit process to split this up into two guys, one from the left of our vertical asymptote, and then one from the right of our vertical asymptote. We'd evaluate them the same way. We need to be careful, though, when we're plugging in 0 from the right, 0 from the left. Make sure that we keep track of the positives and negatives. So 0 from the left is a very small negative number squared, becomes a very small positive number. Times 2 is still very small and positive. Divided by, this ends up being negative infinity. I plug in negative 1. That's 1. This is negative 1/2. Plus, I plug in 2. I get negative 1/8 minus. I plug in 0 from the right. Again, I will have a very small positive number times 2 very small positive number under negative 1. This is minus negative infinity. Unfortunately. Well, we end up with that being positive infinity minus infinity, which we don't know what it is. I probably need to do a little bit more work to show that this is divergent. But you get the gist of it. Okay, so you'll find that these problems aren't super hard. They're just more ways to test you on your antiderivative techniques. So make sure you understand your antiderivative techniques. And guess what? Don't forget about all that polar stuff we did, which seems like so long ago. That's on the test too. This is 5 lessons in this unit. We're not used to this, okay? So lots of studying, but guess what? Long weekend to do that. All right. Well, you don't have a long weekend, but you know what I mean.